Welcome back. We will now consider another problem another set of examples on what we have been discussing so far. So we have here some worked examples. And the first problem here says solve the equation z cube plus 64I equals 0. Okay. So we want to solve this equation that says z cube plus 64I equals 0. So let's see how that works out. Of course, given that z cube plus 64I equals 0, in this case, we can see the only unknown here is z. Okay, I is not an unknown. I is our complex coefficient, which is root of -1. So the only unknown here is z cube. And to deal with this, what we simply do is make z cube the subject of the formula. I mean, this is similar to trying to solve a polynomial with complex coefficients. So in this case, we have 64I as the constant part. So if we make z cube the subject, we see that it follows that z cube will be equal to minus 64I. And from that, it means zh that we are looking for will be equal to the cube root of minus 64I. So this problem is another way of asking you to find all the cube roots of minus 64I. It is equivalent to simply saying find the cube root of minus 64I. So that means we have a complex number here. I want to get all of its cube roots. Okay, so let's get right into it. So we can say let let this be z. Okay, so we can say let's call that z star be equal to minus 64I. So we'll come back to take the root of that. Of course, this is equal to 0 minus 64I, implying that the real part of this is 0. So with that, we now know that our modulus r, okay, which is modulus of z star. Okay, why am I calling it z star? Because the question originally provides for z, so I don't want to I want to avoid mixing them up. That's why I've called this z star. Okay, so this is going to be equal to the square roots of the real part 0 squared plus the imaginary part minus 64 then squared. So obviously this is going to be just 64 at the end of the day. And we can get the argument of this by locating these on the argand plane. We know that we have something like this on the argand plane. This is the real line, this is the imaginary line, and we have 0 on the x-axis. Okay, and on the imaginary line we have minus 64, so that should be somewhere around here, negative 64, and that means the number is at this point. So if we connect it from the origin to this point, we have this line, and the angle that it makes with the positive x-axis is this. Okay, so that means that our theta is 90 degrees, which is pi over 2. Okay, negative this time around because it is clockwise from the positive x-axis. Okay, so we have the modulus and argument of z star. Okay, that is to say that argument of z star, which we are denoting as theta here, is equal to minus pi over 2. Okay, of course, our calculator could have provided this information for us directly. Okay, so with this, we want to get a cube root of this. So we now say that there's z star, let's write it out in polar form, is equal to, so we've seen the modulus is 64, so in polar form z star will be equal to 64 over, so we have that to be cosine of theta, that's cosine of minus pi over 2 plus I multiplying the sine of minus pi over 2, and we'll close the bracket. So with this, we can now find out what the root of So this is it. And z, which is equal to the cube root of 64I, is equal to the cube root of z star. So this is cube root of z star. And for us to get that now, we know that the cube root of z star is given by, so from the formula for the nth roots of a complex number, then we know that we have q sub k equals r, okay, to the power of 1 over n. So in this case, our n is 3 because we are interested in the cube root. But let's write out our general expression first. This will be then into cosine of theta plus 2 pi k divided by n, then plus I sine. Then we have this to be theta plus 2 pi k, then divided by n. So put all of this together, and we know that in this case, in general, k should go from 0 to 1 to n minus 1. So, okay, 0 to 1 and so on and so forth up to n minus 1. So here we know that theta is equal to pi over 2. R is 64 as we obtained up there, and we are also interested in the cube root of the number, okay, the cube root of z star. So by that, our n is equal to 3. Okay, so that we can now get the cube root that we're interested in now. So we now have this to be, so let us have a new page after that. So we now say that therefore our z, okay, so that z that we're interested in, don't forget z is in this case the same thing as the cube root, okay? Z is the cube root we're interested in. So we can now say z sub k is equal to, so why am I using z instead of this q sub k? Because our original equation here has z as the unknown. That is what we're looking for, okay? So it makes no difference. It is just a change of variable, like I'm substituting for putting z here in place of q, okay? And this is going to be r, which is 64, okay, to the power of 1 over n, which is 3, then into the cosine of theta. Theta is minus pi over 2 plus 2 pi k, and this is divided by 3, then plus I sine minus pi over 2 plus 2 pi k divided by 3. So we have all of these put together here, and by that we can now say the first root, that is z0, that is going to be equal to 64 the power of 1 over 3, and this is multiplying the cosine of minus pi over 2 plus 2 pi of 0, then everything here is divided by 3 plus I sine minus pi over 2 plus 2 pi k plus 2 pi k, that's a 0, divided by 3. So put this up and close this off. So with that, we are good to go. We can just put this in modulus argument form or simpler form, please, of a complex number. So we're going to have this to be 64 to the power of 1 over 3 into the cosine of, so this is minus pi over 2, and then this is 0, and then this is 3. So this is minus pi divided by 2 times 3, which is 6, and then plus I sine of minus pi over 6 as well. So this is the results we get for the first part. This is our z sub 0. And so what do we call this? Can we have this in short form so that we just write out the results in short form here as well? Okay, so we know anyhow that goes is fine. We know that we can easily get, let's see, the cube root of, where is that? The cube root of 64, that should be some number, that is 4, okay? So this right here is 4. And then the cosine of this, so let's get the cosine of minus pi over 6, the cosine of minus cubed, and then pi, and this divided by 6, and then we'll put to close this off, then plus I multiplying sine of minus pi over 6. So we have minus and then shift and then pi, and then this is divided by 6. So we have this here and then we have this here. So that is root 3 over 2 minus 1 over 2i. So 3 over 2 minus 1 over 2i. So we'll multiply that by 4. Okay, 4 is outside here. So we'll multiply everything there by 4. Let's change this to, let's put a bracket here, then put a bracket here, then put 4 out here. So let's see what that gives us. So 2 root 2 minus 2i. So this is one of our results. 2 root 2 minus 2i, right? 2 root 2, 2 root 3, please. 2 root 3 minus 2i. 2 root 3 minus 2i. So this is one of our results for z, and we can get the other results by just going on with the values of k now. So we know that you can set k equal to 1 to get z1. So when k is equal to 1, this will be equal to 64 to the power of 1 over 3. So we have this to be 64 to the power of 1 over 3 into, what does that give us? So we just write 4 here directly, okay? So this is going to be 64 to the power of 1 over 3. Yep, yeah, let's leave it here this way. So this will be cosine of minus pi over 2 plus 2 pi, okay, into, this time around we are using 1 for k, and we divide all of these again by 3. So we have something like this, and this is plus I sine minus pi over 2 minus pi over 2 plus 2 pi into 1, then divide everything here by 3. So we close this off and close this off. So with that, we are good to go. We have an expression here for the result when we have minus pi over 2 plus 2 pi. Okay, it's 2 pi plus pi over 2, that is 3 pi over 2, and then we divide that by 3. I mean 2 pi minus pi over 2, that is 2 minus 1 over 2. 2 minus 1 over 2 is 3 over 2. And then we have 3 over 2 divided by 3, that is 3 over 6, okay? Basically, or say 1 over 2 at the end of the day. So basically, what we get from this is going to be z1 is equal to 64 to the power of 1 over 3, that is 4. So this is going to be 4 into the cosine of pi over 2, then plus I multiplying the sine of pi over 2. Okay, so this is the result of this. And we can put this in sort form as well. I mean, like in this form, x plus iy. How did I come about this? Again, 2 minus 1 over 2 is 3 over 2. That's 1.5. So that is divided by 3. Then that's going to give us 1 over 2. So this is pi over 2 altogether. And then if we change all of this to pi over 2, okay, that was the reason I avoided having to use the calculator for that part, so that we don't have to wipe this off and we just get it here directly when we insert this. So this is pi over 2. Let's come here and change this. So this is pi over 2, and then this is giving us 4i at the end of the day. So 4i is one of our results. 4i. So with that, we are good to go, good to go, good to go. So this is giving us z1. And lastly, when we make k equal to 2, we have z sub 2 to be equal to 64 to the power of 1 over 3 into the cosine of minus pi over 2 plus 2 pi into 2, because k is now equal to 2, then everything here is divided by 3. Then we have plus, what will this give us? This is I sine minus pi over 2 plus 2 pi into 2. Then everything here is divided by 3. So we close this off, and this gives us 4 into, so let's see what this argument will be. This is this is 4 pi, so that's 4 minus 1 over 2. 4 minus 1 over 2, that is 8 over 2, minus 1 over 2, that is 7 over 2. Then divide by this, that is 7 over 6 at the end of the day. So basically, this gives us the cosine of 7 pi over 6, then plus I multiplying the sine of 7 pi over 6. Okay, so we close this off and close this off. So that's our z2. Okay, but this is out of range because this is greater than pi, so this is not a proper way to put it if we want to have a standard argument. Okay, this is fine, it's correct. In case you just want to get it in form of x plus iy, this works totally fine. It gives you the same result as having to standardize this argument. So if I'm going to standardize this argument, then it is good that we just subtract minus 2 pi from this so that the argument becomes standard without changing the values of the trigonometric ratios here. These are the values of the sines and cosines uh, here. So this is going to be equal to minus 7 pi divided by 6, sorry, 7 pi divided by 6, then minus 2 pi. Then we have plus I sine, this is going to be 7 pi divided by 6 as well, minus 2 pi. Then we'll close this off and close this off. So what do we have left? This is going to be equal to 4 into the cosine, so 7 pi over 6 minus 2 pi. So that is synonymous to 12 pi, okay, minus 7 pi. Negative of that, 12 minus 7 is 5. So basically, we'll be having the cosine of minus 5 pi divided by 6. Okay, then plus I multiplying the sine of minus 5 pi divided by 6. And that is the standard arguments, okay, for z2. And with this, we are good to go. Let us now insert this in the equation here so that we can have a result in another format. So the form a plus ib. So this is minus 5 pi minus 5 pi divided by 6. Then we have this to be 6 in the denominator. Numerator we put minus 5 pi divided by 6. So that's minus 2 root 3 minus 2i. Minus 2 root 3 minus 2i. Minus 2 root 3 minus 2i. Okay, so with that we are good to go. This is another solution to the given equation. So these are all the solutions to the given equation. Okay, in polar form, this is the expression for that first solution, and in the form a plus ib, this is the expression for the solution as well. So that's what we've done here for all of these terms. And that means that when we take any of these and raise it to the power of 3, we'll be getting this result, which is 60 minus 64i. Okay, so we can check that out for each one of them, raise them to the power of 3, and we get minus 64i. Okay, so that is that as per. Okay, let us have a check of this thing. If I'm going to raise it to the power of 3, we'll be raising this to the power of 3 as well. 64, 4 to the power of 3 is 64. So this portion is guaranteed to give us 64. Okay, so that means if we raise this as it is here to the power of 3, we will be getting minus I from that, so that at the end of the day everything here will be equal to minus 64i. Okay, and of course that is evident for this one. By the time we raise this to the power of 3, for instance, raise this to the power of 2, this will be 16, then I squared, and that is minus 16. Then when we multiply minus 16 by 4i, 16 multiplying 4 is 64. Then multiplying that by minus I, so that gives you minus 64i. So it's evident that the cube of this is going to be minus 64i. So for this, we can easily check if we put in, okay, this was the last result we obtained. If we squared it, so the square of the answer that we just obtained now and multiply by itself, you know why I'm doing that? Because the calculator cannot possibly have this. to the power of 3 directly. So that's why I'm doing minus 2. And we have that minus 2 root 3, then minus 2i minus 2i. So we close this off and see what it gives us. So it confirms that indeed the cube of that is minus 64i, okay, as expected. And for this as well, we can do the same thing. We can have 2 root 3 minus 2i, 2 root 3 minus 2i, okay, to the power of 2, and then multiply the result by 2 root 3 minus 2i again. So there's no I there. Let's also go back and start I. Then this is 2 root 3 again minus 2i. Let's get out of the square root sign. So this is 2i. Then close this off, and that is minus 64i as expected. So that is all for the solution to this first problem. So before we end this lesson, let us have another example. And that will be let's have a look at another problem. Okay, that's a better way to say it instead of saying let us have another example, because all we have are problems and problems and problems. Oh, you might say, oh, I don't have problems. No, you do. You do have problems. We all have problems, okay? And this is our problem right here that we're trying to solve. Well, I mean, this is one of our problems that we're trying to solve here. So this is this question or this problem says solve z, what is this? Z squared into, so this is z squared into 1 minus z squared, and so is equal to 16. So we have another equation here. In terms of z is the unknown, and we want to solve this, okay, for z. You can see this is looking quadratic. It looks quadratic because we have z as we have z to be squared all through. But don't get carried away. This is not quadratic because z squared is multiplying some expression that contains z squared. So by the time we clear that off, that is no longer quadratic. So if it were quadratic, and then of course we have real coefficient, I mean we wouldn't have to I mean we could just use the calculator for that and get the result directly. Okay, but in this case, let's move on and say given that we have z squared into 1 minus z squared to be equal to 16, then it follows that when we expand this out, we have z squared, that is z squared multiplying 1, then minus z squared multiplying z squared, that is z to the power of 4, is equal to 16. And with this, we can say that we have z squared minus 64 minus z to the power of 4 equals 16. So we can rearrange this. I just want to make it look quadratic some way. So I want to move this to the other side. So this is going to be z4, z to the power of 4 plus, and then this is going to be minus z to the power of 2. Then we have plus 16, and everything here is equal to 0. So basically, what we want to do here is to solve as we would polynomial equations with real coefficients. Okay, this is a polynomial equation with real coefficients, and so all of the techniques that we would typically apply to solve equations with real coefficients when dealing with real numbers, okay, will also be applied here, except that we bear in mind that whenever we need to take any route, it will give us multiple results, and we have to capture those multiple routes using the methods we have established so far. Okay, so because of that, in this case, it is obvious that we can use some other letter, say Q, say R, say whatever you want to use. Okay, I think normally I would use Q for this, but we already have Q being used for something else, for our general expression for the nth root of z. So I want to use P here, so I will say let P be equal to z squared. So why am I doing that? I can see this is power of 2, this is power of 2 all squared. So if I make this substitution, then this equation will become quadratic evidently. So we can then solve that, get the two roots of that, and keep it, then come back to use that to get p. Okay, so let p be equal to z squared, so that p squared, when we square p, is going to be equal to z to the power of 4. Okay, and when that happens, we will now have p squared minus minus p z squared, which is p, is plus 16 is equal to 0. Okay, so that is the idea with that, and this can be solved now using, maybe you're using a quadratic formula. That is fine, it works perfectly. You can also use your calculator, that may be acceptable, because I mean, this is just by the way to many things we still have to do with this equation. So either of them is acceptable. I want to use the quadratic formula, so just that is, I mean, the closest that we can have to a manual solution. Okay, so we now say by this, therefore, we now say P will be equal to, don't forget how this works. We say that I want to write that out formally first. Recall that the solution to the quadratic equation, ax squared. So if you have the quadratic equation of ax squared plus bx plus c equals 0 is given by this quadratic formula. Okay, some people call this almighty formula. That is not acceptable here. Please, I wanted to say grow up and stop doing that, but I don't want to insult anybody, so please don't do that. Okay, so this is minus b plus or minus roots b squared minus 4ac, then all divided by 2a. So that is the idea. So that's what we can just use here to get manually obtain the solution to this. So we now say that thus um, p squared minus p plus 16 equals 0 as the solutions, because this will give us the two results. We know that when I'm solving a quadratic equation, we should expect two results. Yes, that is all. It captures all of the results, whether it's going to be complex or real. This takes care of everything for us. Okay, so then we're going to have p to be equal to, so in this case, comparing to this form, we know our a, that's the coefficient of the square term, is 1, and our b is the coefficient of the linear term, that is minus 1, and c, the constant, is plus 16. So we can say this is minus b is minus 1, so we have minus of minus 1, then plus or minus the root of b squared. So b in this case is minus 1. So this is minus 1 squared minus 4 multiplying a. A is 1. Then multiplying c. C is 16. So with that, we are good to go. And then we divide everything here by 2a. All of this divided by 2a. And then this is 2 multiplying 1. And at the end of the day, this is going to be p equal to, we have p to be equal to minus of minus 1, that is 1, then we have plus or minus, then we have the root of 1 squared. So let's forget about all of this, please. So let's get rid of all of these. This is just 1, okay, plus or minus. So we can just insert this in our calculator now and see what it gives us. Yes, so this is in complex mode, so it will give us error. If it's in normal mode and insert this, it will give you error, but in complex mode, that works just fine. We know this is going to give us negative here under the square root sign. So which, if we were dealing with real numbers, we would say, oh, this will not have a solution because it's not going to give us a real number. But here, we know we are dealing with complex numbers, so whether it is real or complex, it is a solution. So we're taking everything. So this is going to be 1 minus 4 multiplying 16. That should be 64. So 4 multiplying 16, and that is 3 root 7i. So what we have here is 1 plus or minus 3 root 7i divided by 2. So this is 1 plus or minus 3 root 7i. Then all of this is divided by 2. Okay. So that means that is to say that there are two solutions here. The first one is p equals 1 over 2 plus 3 root 7 over 2i, and the other is that p equals 1 over 2. I hope you know how I came about that. 1 divided by 2, then we take the plus, and the other one is with the minus. So this is 3 root 7 divided by 2, then I. So with this, we are good to go. Of course, I said we could just solve this with our calculator, so I want us to check that. We could have solved directly with a calculator. I'm showing you this, so in case you needed to show how you arrived at the result, you know precisely what to do and how to do that. So that's why I've gone through this manually. So to use the calculator, we just solve the equation. It starts this coefficient. A is 1. B is minus 1, so that's what the same thing the calculator does under the hood. So this will press equal to, and then for the next one we get 16, and then we go here. So it tells us the first result is 1 over 2 plus 3 root 7 over 2i, which is what we have just obtained, and then, the next one is 1 over 2 minus 3 root 7 over 2i. Okay, so we're good. So anyhow you approach to that, you would get the same thing. Okay, so that saves you time where it is not required to show all of these workings. Okay, now we have an expression, I mean, we have results for P. Don't forget that P is actually Z squared. So that means we have just obtained what Z squared should be. Okay, so thus we now know that Z squared is equal to 1 over 2 plus 3 root 7 divided by 2i, or z squared is equal to 1 over 2 minus 3 root 7 divided by 2i. So we now pick each of these and get the solution to it. I mean, get the square root of each of them. So basically, this is saying that z squared is equal to the root, sorry, z now will be equal to the root of this, the root of 1 over 2 plus 3 root 7 over 2, then I. So, or z will be equal to the root of 1 over 2 minus 3 root 7 over 2i. So that is what we want to get now. So this will give us, I mean, the root of this will give us 2 results. This will also give us 2 results. So at the end of the day, altogether, those will be giving us the 4 results we expect from this equation, because the power here is 4. This is a 4-degree polynomial. The solution should be 4. And we expect that because the coefficients of these polynomials are all real numbers. Okay, so I will know that for polynomials with real coefficients, the roots will occur in conjugate pairs. Okay, so we expect that by the time we take the roots of these, okay, and also the roots of these, we should expect that at the end of the day, the 4 results we are getting will occur in conjugate pairs. Okay, so let's go right ahead and deal with this one after the other. So for that to happen, I can say let z1, okay, be equal to, I want to use this here, z1 equal to 1 over 2 plus 3 root 7 over 2i, and then let z2 be equal to 1 over 2 there minus 3 root 7 over 2i. So with this, we can now get the roots of what we have here. So basically, this is going to be equal to z z1, so we have this to be z1, and we can say r1 will be equal to the modulus of z1, and that is going to be equal to the root of the square of the real part plus the square of the imaginary part. So we have this over 2 when we square that. It is actually going to be equal to it is going to be equal to r2 as well, because the only difference is that this one has negative. If we put that here and square it, it will give us the same result at the end of the day. So let's just get the modulus of this. Okay, so we can just say which of them is easier to do. Let's just use the absolute value function. I love to look at the fastest, okay, or take the laziest route. Okay, so that is plus, and then I have 3 root 7, 3 root 7, then divided by 2, and then I put the I right there. So I want to get the modulus of this, so it tells me the modulus is 4, okay? So that is that about that. We're getting 4 from this. We know that is the same thing as R2, which is modulus of Z2. So they have the same modulus, the same moduli, if you like, and they are as per the argument for Z1. So we can show that here on the argand plane. So this is the real line, this is the imaginary line. Z1 is 1 over 2 and 3 root 7 over 2. So we have this to be positive, say 1 over 2, and 3 root 7 over 2 also positive. So 3 root 7 over 2. So we'll trace this out and trace this out. We see the complex number will be located here. And the line from the origin to this point is here. So the argument is here. So we can call that theta 1. So we'll have theta 1 to be equal to the tan inverse, that is quite easily the tan inverse of y over x. Y is 3 root 7 divided by 2, and our x is 1 over 2. So by the time we do this, 1 over 2, we cancel this out. So basically, our theta 1 is tan inverse of 3 root 7. So we can take care of that as the tan inverse of 3 root 7. Let's see what that gives us. Tan inverse of 3 root 7, then come here and close this off. So that is giving us 1.4 blah blah blah. So I want to avoid writing out something like this. It doesn't look like something I want to write out because this is giving me some sodic expression and I don't like it. I don't like that. So what can I do if I don't like that? I just leave it like that, okay? I just want to leave it like that. And I can get theta 2 as well, similarly. So I just know that this is tan inverse of, so theta 1 is equal to the tan inverse of 3 root 7. Okay, I don't like the size of that long fraction. It's going to make me it's going to make us lose sight of some values, okay, with unnecessary approximation. So I want to avoid that as much as possible. So with that, we are good to go. And what is the next thing? We want to get the argument for the second one. It's going to be similar to this for Z2. We have this is the real line, this is the imaginary line. Okay, we could have shown everything here, but of course, no problem. So this is 1 over 2, and the other one is minus 3 root 7 over 2. So minus 3 root 7 over 2 will be here, minus 3 root 7 over 2. So the angle will be the same, the only difference being that this is going to be negative. So this is going to be theta 2. Negative because it is taking clockwise this time around. So here we see that theta 2 is equal to the tan inverse of y. Our y is minus 3 root 7 divided by 2, then divided by x, which is 1 over 2. So again, we have the tan inverse of that's just the negative of the tan inverse of 3 root 7 that we have up there. So the argument of this will be negative, okay? And with that, we are good to go. So we can see that the only difference between the two is the values of theta. This one is positive, whereas this is negative. So we can also say that we can also pick these two as one complex number and say that the argument will be plus or minus tan inverse of 3 root 7. That works fine as well. Okay. So now going forward, we want to get the square root. So we can now say that birds z is equal to the square root, okay, of z1, or z is equal to the square root of z2. So if that is the case, then we are going to have zk. So we say so that zk. So z is the root we are looking for now. That's why I'm writing it as zk instead of qk that we have always used. Okay. So the same expression that will be the modulus, okay, of z. So that will be r. So it can be r1 or r2. So I'm just writing it as r to the power of 1 over 2, then into. So this time around we'll have the what is this called now? This is going to be cosine of theta plus or minus, so this is plus 2 pi k please, divided by n. So our n in this case is 2, and then we have plus I sine theta plus 2 pi k, then divided by n, which is still 2. And we close this off, then we know that k in this case will be 0 and 1, okay, because we are interested in square roots. N is equal to 2, so we know our k should go from 0 to n minus 1. So n minus 1 in this case is 1, so it should go from 0 to 1. So that's basically what we have done here, and by that we are good to go, and we can now get what our z should be. Okay, so if we go with the first one, we can say that z naught will be equal to, that is going to be r. Our r is 4, then we have 1 over 2, and then we have the cosine of theta. So theta, as we have it up there, is tan inverse of 3 root 7, okay, for the first one. So I say this is tan inverse of 3 root 7. Then we have plus 2 pi into 0. Then we divide all of this by 2. Then we do plus I multiplying the sine of the tan inverse of 3 root 7. So let me write this on another line. So this is going to be plus I multiplying sine of the tan inverse of 3 root 7 plus 2 pi into 0, then divided by 2. So we close the bracket and close the bracket. And what does this give us now? We have 2 here, obviously. And let's see if this will just give us some results directly without us having to go through another long process. So this is going to be, what do we have here? We have this here. That's what's going to. So this is tan inverse of 3 root 7. This is 0. Okay, this portion is 0. So let's see what that gives us. Let's just write everything in directly. Cosine of, so I want to put this inside. Tan inverse of 3 root 7. 3 root 7. Then come out here, close that and close the second one. Okay, then plus, then I have I multiplying the sine of the tan inverse, so putting tan inverse of 3 root 7, then come out here, close this off. Okay, close this off as well. So let's see if it gives us actual numbers. Okay, this is giving us 1 over 8. The cosine part gives us 1 over 8, which looks good. This is giving us 0.9. I don't like that. I don't like it. It doesn't look good. So 0.992156, blah blah blah. So that's what we get for the sine part, which this was giving us some fraction or such. Okay. So but that's 0.9921567416, blah 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 I. So that is the results we are getting from this, having put this as 0. Okay, and sorry, we didn't divide by 2. Okay, so this tan inverse should be divided by 2. Okay, yep. Okay, let's divide that by 2, divided by 2. Yes, so let's see what that gives us. 3 over 4. This side is still giving us this. Okay, so this is 3 over 4. 3 over 4, then plus, what do we call that? We have 0.6614378278. 0.661437, 0.6614378278. 8278. Okay, I might be wondering why am I writing out everything. So you might want to write out the first three, but I don't feel very comfortable with that because of the approximation. Yes, this may have also been approximated because that's how far the calculator can display it, but it's okay. So we just leave it as that, as this is our z naught. Okay, so that means that this z naught should satisfy the given equation. So, and we can check for that here. So let us say that, so let's clear the screen here. then we'll put in this z. Okay, so this is alpha, then we have x, then into, sorry, that is x squared. Okay, so let's say x is taking the place of our z here, into 1 minus then alpha, then I have x and then squared, and then we close this off. So if we bring this to that side, that is minus 16. So let's see if when we substitute what we just obtained now, we will get 0. Okay, so I want to put in the answer we just got. So it is giving us, this is not giving us 0. That is not giving us 0. Okay, that is not giving us 0 because the result we just obtained now is for this part. Okay, it's for this portion. Okay, we have to multiply that result by 2 before we used it. Okay, so this should be multiplied by 2. Let's get back to, oh, I've wiped off everything. So this ought to be multiplied by 2. We can see there is 4 to the power of 1 over 2 here, which is 2. So we should multiply this by 2 and see what it gives us when we do that. So let's get back to the expression. 2 is out here. Okay, so let's put 2, then close this bracket, then put the cosine of everything we have here. Cosine of let's see, shift, then tan inverse of 3 root 7. So we have 3 root 7. Then we come here and close this off and divide by 2. Then we come here and say we have this here, then plus I multiplying the sine of, so we have the tan inverse of 3 root 7. So we have 3 root 7. We come here and close this off and then divide everything here by 2. Then come here and close it off and then close off the big bracket and close off the next bracket. I think that is okay. There's an error. That is too much of that. So this is the result actually. So this is what we should get. Okay. So that is after we have multiplied by 2, it should give us this. I mean, 3 over 4 multiplying 2, that's 3 over 2. So we have 1.32287576565 blah blah blah. So that's all you can get from that. So that is 3 over 2. So this should be 3 over 2 after having multiplied by 2. Okay, or we can leave it this way and put 2 outside. That's 4/2. So this is 3 over 2. And we have for this part, for the imaginary part, we have 1.132287566. Okay, 1.32287566. Okay, right. So 1.32287566. Okay, so we should see that that satisfies the given equation if we check that out. So that is going to be, so let's get to the given equation now. Okay, I will come back to that. Come back to that. I don't want to wipe this thing on the screen off because we need to get the other roots as well. Okay, so by that, z1 then will be equal to the same thing. This is going to be 4 to the power of 1 over 2. Then we have the cosine of the tan inverse of 3 root 7, then plus 2 pi into 1 this time around because we're substituting k equal to 1. We used k equal to 0 here. So using k equal to 1 here, then we'll divide this by 2. Then we close this off, then plus I multiplying the sine of the tan inverse of 3 root 7. So we have 3 root 7, and then we have plus 2 pi into 1, then divide everything here by 2. So what does that give us? At the end of the day, we close off this bracket. So we can get back to the expression we still have on our calculator and just insert these values. Okay, that means we just add 2 pi to that portion of tan inverse of 3 root 7. Okay, so we just come here and add 2 pi to this. We have plus 2 and then shift and then pi, so that works. Then come here and add 2 pi to this as well, so this is plus 2 and then shift and then pi. So that is that about that because we have 2 pi here now. So this is giving us minus 3 over 2 minus, so this is giving us the negative of this as expected. We know when we square this, it will give us the same result as when we square its negative. Okay, so this is minus 3 over 2 minus everything we have here I. So that means z1 is equal to minus 3 over 2 as expected minus 1.3228 then 75656 okay I right we're good. So those are the roots we obtained by considering z1. Okay, we should now consider z2 because I mean both of them should give us results. Okay, so I'm going to continue with that. We know the only difference is that instead of this minus here we should have, I mean, instead of this plus tan inverse of this, tan inverse of 3 root 7 now, we should have the argument to be minus tan inverse of 3 root 7. Now, if I were to guess, I would say that now I should get the conjugate of this, that means minus here, and then I should get the conjugate of this as well with plus here. And those are the two other results I'm expecting to have, okay? But of course, we should show that those are the results. So the only difference now for the next ones is to now use negative of tan inverse of 3 over 7 instead of using tan inverse of 3 over 7 because that's precisely what the argument of this is. Okay, so let's go right into it. So I'm going to, so please, I'm going to write that as z, let's say z star, okay, 0. So z star 0, and that is going to give me, just to avoid mixing it up with z0 that we have here up there, and I don't want to use z3 so that we don't erroneously use 3 k equal to 3 in the expression. Now if we use k equal to 3 we'll get the correct result still. Okay, so you can try that out. It will give you a correct result actually, but I don't want to cause confusion. That's why I just want to use z star here. And we know by the time we have obtained all of the results, we put them all together. So this time around, we're going to have r, which is still 4 to the power of 1 over 2 into the cosine of theta. So our theta in this case is minus of the tan inverse of 3 root 7 then plus 2 pi into 0 then divided by 2 because we're taking the square root of that as well, plus the next part is I sine, then we have again minus the tan inverse of 3 root 7, then this is plus 2 pi into 0, and then we have this all divided by 2. So that is the result we get from that. And we know, so we're going to write that out here and we're done. I want to get z star 1. You should know why I'm doing that as well, because I want to avoid wiping off that plus 2 pi that we have on the calculator screen right there. So I want to write this out so that we get this first before we move on to the other part. So this is into the cosine of minus the tan inverse of 3 root 7 then plus 2 pi. In this case, k is equal to 1, so this is into 1. And then we divide this by 3, and then we have plus. Then this is going to give us I sine. Then we have minus the tan inverse of 3 root 7 then plus 2 pi this time around into 1 again, and this is divided by 2. So we should expect that this here will be negative of what we have here, okay, which should be the conjugate of the second result of them. So with this, we are good to go. We just get into our calculator and change this, okay, instead of using this tan inverse of 3 over 3 root 7, we just put negative of that there. So this is minus. Ensure that the minus is with tan inverse. You don't put it outside. If you're putting it outside here, you're taking minus of everything you have inside. That will be giving you a wrong result. Okay, so minus of this tan inverse, it has to stay with that tan inverse. So let's see what that gives us. So as expected, that is a what is now, that's the conjugate of this result. Okay, so that's the conjugate of the second one we obtained here as expected. So that is for this. Though we have just done this with 2 pi, we can see there's 2 pi there. Okay, so that's the second result that we just obtained. So this is minus 3 over 2 plus, what is this thing here again? Okay, I think it's faster to just check it out calculator again. 1.33 and 1.3228765. Okay, 1.3228765. 87,565i. Right. Then let's go up there and get for this one. So we just go and remove those two pi's. Well, in this case, we have 2 pi multiplying 0. So we just get rid of this and go there also and get rid of this 2 pi. So get rid of this. And at the end of the day, we have 3 over 2 minus this, which is the conjugate of the results, the first part of the result we had up here. Okay. So this is basically 3 over 2 minus 3 over 2 minus, what is that again? 1.322, okay, 87,565i. Right. So that is our result. So these are all the results which are actually solutions to the given equation. Okay, we're going to bring them all together. Okay, but I want to just highlight them here. This is a solution to the given equation. This is another solution to the given equation, and this is a solution to the given equation as well. This is telling us z naught star is equal to this. And finally, this is also a solution to the given equation. Z1 star, okay, is a solution. So with that, we have all the solutions that we need, okay, all the solutions to the given equation. And of course, we can summarize this. We know this is z0 here is a conjugate of z0 star. Yeah, so we can write them together. So we can now say that therefore z is equal to 3 over 2 plus or minus, okay, plus or minus is how we can put those two results together in one place, okay. So of course you can list them all out again and say that's your result, but it's fine. But I know 3 over 2 is plus or minus this, plus or minus 1.32287,565i, and z is also equal to, so or z is equal to minus 3 over 2 plus or minus the second one 1.32287,565i. Okay, so that is our result to the given equation. So any of the four results here will work perfectly for the solution as solution to the given equation. So let us now verify the solutions. So we enter the given equation and then calculate with these values that we have. Let's just see that it satisfies, or they satisfy, any one of them will satisfy the given equation. So we say alpha, then x, then squared. So we're using x in place of z here. It makes no difference. That's just a variable. So we have, I don't change that. So this is 1 minus alpha x, then squared, then we'll close that. Now bring 16 to the other side, or leave 16 as it is and calculate and see that the result gives us 16 when we calculate for each of them. So I want to calculate for the last answer we obtained. So you see that it gives us 0. So that confirms that that last answer is a solution to our equation. Okay. You can confirm for the rest also. You will get the same result actually. So that is that about that. What was the last answer we got? This was the last answer we got with our calculator. So you can confirm for the rest. Okay, when you get let's say 3 over 2 plus all of these blah blah blah, let's enter them as they are. This might be something in short form, I suspect, but we don't have that detail here, so we can just leave it as it is. Then let us see if we could have obtained this in short form, this part in short form. So we've confirmed that for one, I can assure you that it works for the rest. So check for yourself and see that the others also satisfy the given equation. Okay, and I said let's find a way if we can possibly have this in short form. I would really prefer that. I don't like the size of this number. Okay, and if we would do something like that, let's do it separately and see if it works. We're going to get the sheet and then tan inverse of 3 root 7, then close the bracket there, divide the result by 2. Yep. Then come here and close this off. Let's see what it gives us. So that doesn't work. It doesn't give us a sort result. Doesn't give us a sort result. So let's change it to a normal mode. Let us repeat that. Okay, let's clear that up. That's the sign of the tan inverse. So sheet and then tan inverse of 3 root 7. Then we'll come here, close the bracket, then divide everything here by 2. Then come here and close this off. And see, okay, it still gives us that number. All right, so I guess I have to work with something I don't like now. So that's some character training. Okay, so that's all for this lesson. That's all the solution to the equation we have at hand. So this shows you how you should deal with it, of course. This means that if you had a calculator that was capable of solving a polynomial equation up to the fourth power, you could have obtained all of the results that we obtained here, okay, using that calculator. So it's going to work perfectly. You get your results and just move on, okay? And if you were in a situation where you don't have to provide all the details as to how you came about the results, once you have obtained these first two, you have obtained the others as well, because the others will just be conjugates of this. The reason being that, as we pointed out in the previous lesson, the solutions, that is the roots of a polynomial or the zeros of a polynomial with real coefficient. This is a polynomial with real coefficient. They are always occurring in conjugate pairs when they are complex. So the complex roots of a polynomial is always in conjugate, or they are always in conjugate pairs. So once you obtain one result, its conjugate will also be a result, okay, will also be a solution. And once you have obtained two different results here, different because this is plus, this is minus, so they are not conjugates of each other. We know they are different. So we know that the conjugate of this will be a solution as well, and the conjugate of this will be a solution as well. So with that, you don't have to go through that extra stress of trying to find out what the other two solutions are in a situation where you don't have to show how you came about the results. Okay, so that's that for this lesson. I'll see you in the next lesson as we consider another set of equations in complex variables like this. Okay, thank you for watching.